Good morning, everybody, and thank you for coming after a good lunch. I want to thank Coaxial management for inviting me here to give the talk. The talk that I will give in this 15 minutes is about a program that we are doing together with Coaxial and with some other partners, and it is related to having a transparent cathode on top of OLED. And carbon nanotube is a very good material if you can control the dispersion of the material to put on as a transparent cathode, because you can control the transparency, you can control the conductivity, and above all, you need to control the work function, as we will talk in a minute. So the outline of my talk will be just a brief, the end use of a single-wall carbon nanotube as a transparent electrode, especially transparent cathode. Then we'll go to the role of the work function, why it's so important in the case of a cathode, which is unlike anode, how to dope a single-wall carbon nanotube. We also did some work with graphene, so I will show it to you. And also a possible combination that I will elaborate on, which is between graphene and carbon nanotube. And on the end of my presentation, I will show you one example that we are using a carbon nanotube as a transparent cathode. Okay, generally speaking, this is an old view graph of Coaxial describing the application of carbon nanotube for transparent electrode and other application, when as a function of the transmittance as a function of the surface resistance or the sheet resistance. So on the high resistance, we see the icing smart window application, and hence we are reducing the surface resistance. We can go to touch panel, OLED, solar cell, and of course, as we much reduce the resistance, we can go to EMI shielding and so on. So we will talk about this area, which the area of the touch panel, OLED, and other stuff. When we are talking about electrode, transparent electrode, we have to define between anode and cathode. In anode, we have to put the emphasis on high lateral conductivity, namely the very low sheet resistance, and high transmitters of light. In our case, it's in the 550 nanometer. But when we are dealing with the cathode, then we have to go and see another parameter which is very important, and is to control the work function of the material. The work function basically says, I will say it in lame word, how easy it to inject electron to the device that we want to work with. So if we will look at this table, we can see that ITO has a transmittance of about 90% with a sheet resistance of 10 to 30 ohms square, and the work function is quite high. This is the reason why ITO is served as anode, not as a cathode. The same thing with a single-wall carbon nanotube, and the same thing with graphene. The work function is quite high, namely in the range of 4.4 to 5 electron volt. And as I mentioned, in order to serve as a good cathode, we need to reduce the work function. And you can see here the reason for that. And the reason for that is that if we want to inject electron from, let's say, a cathode to OLED section, as you can see over there, then in this case, we have to basically go over a barrier, which, let's say in the case of the carbon nanotube, it's a barrier between the 4.5 or maybe 5 electron volt to the 2.4 electron volt. If we can reduce this barrier, then we will not have to apply so much voltage or so much bias in order to overcome this barrier. So the idea is to reduce the work function of the carbon nanotube in order to level it with the work function of the OLED in this case. Another method to do it is to do a staircase. What we call a staircase is to take, for example, on the right-hand side, we can see that there are two metals, one with a regular work function like argentum, like silver, 0.3, and then we take another metal, which is a very reactive metal, the calcium, which has a work function of 9.2, and then we can moderate the transfer of the electron from the cathode to the OLED. So the basic idea is to see how we can reduce the work function, as you can see on the left-hand side. And the way to do it is usually with the doping of the carbon nanotube. But we have to take into account that we have to maintain the other characteristics of the material, like transparency and, of course, electrical conductivity. Here you can see some example that we did with the axial to coat in different type of transparency a piece of glass with different density of carbon nanotube in order to control the transparency and to control the lateral conductivity. But then we have to also, as I said, to control the work function. So generally speaking, you can see here an example of what is the equivalent work function that we get with the staircase of calcium and argentum and calcium. And our initiative is to take the carbon nanotube to be equivalent to the combination of calcium and silver. So here you can see some example what work function, reduction of work function can do in terms of injecting the electron. Here you can see a structure of a OLED where people put a CNT on top of the OLED and they doped it with the cesium carbonate. And the cesium carbonate basically reduced the work function. And you can see on the right-hand side that when this carbon nanotube was doped with the cesium carbonate, the ability to ignite the OLED is much easier, and the OLED start to emit at a much lower bias compared to the case that the OLED are not, that the carbon nanotube are not doped. All the carbon nanotube can be implemented usually using Dr. Blade method or spray coating. We usually use the spray coating, and we are trying to use printers like ink printer. You can see here an example of ink printer that we are working today of how to manipulate the carbon nanotube and other nanomaterial in order to spray them on the surface and to turn it into carbon nanotube. So as for the doping, we have to end-dope the carbon nanotube in order to reduce their work function. There are several candidates for doping elements. You can see here the silver, arsine, lithium, nitrogen, and phosphorus. And there are also some other alternatives to dope the carbon nanotube, like with the organic component, like the PVP and other dimers. They are what we call molecule doping. As an example here, you can see here how we start the process of increasing the conductivity of the carbon nanotube by getting rid of the surfactant, which is deposit the carbon nanotube, and you can see how the sheet resistance reduce as we remove the surfactant. So this is one move. This is also another system that we did the same thing, and you can see how we can reduce the sheet resistance of the carbon nanotube. Now, after doping, for example, in here we doped it with the nitrogen or HNO3. We can further reduce the sheet resistance to a level that are applicable for cathode. As for the work function, you can see here several examples of reducing the work function with several elements, and you can see here the shift of the graph that basically shows how we reduce the work function from 5 electron volt down to about 3.9 electron volt. You can ignore the Venn diagram over there. They are referring to graphene, which are not relevant to carbon nanotube in this case. Another method is to do molecule doping. Molecule doping, this is work that we are doing today with Princeton University, and basically the idea is to reduce the work function of graphene and carbon nanotube with the dimers. Dimers are molecules that basically it's called molecule doping, and what you can see here on the left-hand side, please ignore the central section, that we, by doping in this case, graphene, and the same thing we are going to do with the carbon nanotube, we managed to reduce the work function to 2.6, which is very, very low. This is going, probably will be published within the next month. And basically, to our understanding, this is maybe the world record in reducing the work function of graphene, and I hope that we will have the same success with carbon nanotube as well. This is the next step that we are going to do with the carbon nanotube. I will just give you an example of how we can implement the idea of putting a transparent cathode as a carbon nanotube on top of a device. This is a device that we are developing in my group at the university, and the basic idea is to have a device that can convert infrared image into visible image. Imagine that you have a very thin foil that from one side you are projecting infrared image, and on the other side you are getting visible image. This process is called the imagery up conversion process. Namely, you maintain the image while up converting the light from low energy infrared into high energy visible light. And the device looks like this. We have a gallium arsenide wafer, which is a substrate and the infrared window. We have absorbing material. In this case, it's lead selenide nano columns. We will not get into it. Then we have a pixelated gold, and on top of it we have OLED, and on top of it we have the transparent cathode, which in this case is single-wall carbon nanotube. And we have to apply bias because we are up conversion, so we have to supplement the difference in the energy from the infrared into visible. So the difference in the energy is given by the external power source. And then we shine the light, the infrared light, and from the other side we are getting basically the visible light or the visible image. I will not get into all the detail because this is not the focus of our talk, but the idea is to have a very thin device so the electron in the hole will have a very short path to do in order to maintain the fidelity of the image. So the device looks like this. This is the structure, and from the Venn diagram device, this is the Venn diagram. The light is coming from the left, the infrared light. It's absorbed in the semiconductor nanosphere, nano columns. It's produced electron in hole. The electrons are drifting toward the anode, and the hole are drifting toward the OLED and the cathode. The electron that go through the anode are injected by the battery to the cathode, to the OLED, through the transparent cathode that we have talked about, and by this means, recombining with the hole and emitting visible light. So the difference in the energy between the photon of the infrared and the visible is supplemented by the battery. Here you can see an example or an animation how this device works. So you can see that we are growing on top of a gallium arsenide a nanostructure, in this case nano pillars or nano columns. We are basically having a dual-sided mirror, which is pixelated. And then on top of it, we are putting the OLED. And on top of the OLED, we can spray coat the carbon nanotube or nanowires or any transparent cathode that we already treated with a low work function, high lateral conductivity, and of course, high transparency. And then we have to apply the bias. We are applying the bias, and then we have infrared light coming from one side, and infrared image is transmitting, and visible image is transmitted from the other side. So this is the principle of the idea here. And what you can see here, the same thing we did with this image show you for the first time the image that we got from the OLED. We shine a very small pixel, and the green, very small green light that you see over there is the green light that we got through the transparent cathode, which is made of the OLED. Then we put it on a optical bench, and we did an imagery experiment, and we shine a 3-bar target. Through a 3-bar target, we shined the infrared light through a resolution target, and then on the other side, we put a visible camera in order to capture the visible image that we up-converted, and of course, that the image went through the transparent cathode. And you can see here how it looks like. These are the images that we got in the visible that were originated by the infrared light, okay? And so by this means, we proved the operation of the up-conversion device, that the light is going through the transparent cathode to the visible camera. So in conclusion, the quest for efficient transparent cathode is relevant in many light-emitting devices. I just showed only one example. In order to do it, beside having a good transparency and good lateral conductivity, we need to reduce the work function in order to get an efficient device. There are different methods in order to dope such carbon nanotube or graphene, and either to spray coat them or Dr. Blade. And we demonstrate 1 electron volt reduction, but recently I show you that we demonstrate 2 electron volt reduction, which is a very good and promising path. And the last comment that I will say, that there is a rationale to make a joint effort of using graphene and carbon nanotube that enforce each other in order to have a transparent cathode. This is something new that we already start to work on. Thank you.
Thank you very much. Any questions? Please. Just a moment. I'll give you a mic.
Thank you very much for that interesting talk. I'm interested in knowing the application of the infrared to the visible device that you showed the working. Yeah.
Okay. This is not the topic of this conference, but I will get into it. There are 3 main applications. The first application, which I think this is the best one, is basically to have a device that is the sensor of a LIDAR in the short wavelength infrared. Short wavelength infrared, namely 1500 nanometer, it's very, very attractive to have LIDAR because it's not in the visible. It doesn't dazzle by the sunlight, and the laser is eye safe. So there is a good tendency to go to a 1500 nanometer spectrum. But the problem is that the detector is very, very expensive. The price of LIDAR today, or the target price, is about $100, but the price of one detector is about $3,000. So there is a discrepancy between the two. What we intend to do is to take the layer, the up-conversion layer that we have developed, and to attach it to a visible sensor. The visible sensor, like you have in your smartphone, costs $2, okay? And then we can convert $2 sensor, which is made of silicon, into infrared sensor. that can work with the LiDAR. This is one application. Second application, you can think of today, all the smartphones are going to dual camera, okay? Dual camera. So we can propose that one of the camera will be in the infrared. And basically, it's the same camera. The only difference is that one has this layer that coat the surface. And third application is, for night vision system. You can think of night vision glasses that work in the infrared. They are very compact. And, for a homeland security application. So maybe these are the three, I would say, most advanced applications.
Thank you very much.